All right, welcome everyone. I'm delighted to introduce Professor Olga Russakovsky. She's a faculty member in computer science. She's an expert in computer vision, AI fairness, among many other topics. I've worked together with her for many years and I've learned so much from that collaboration. Let me describe her research in this way. Many of you who are students perhaps who have entered the AI field wanting to work on deep technical problems might have a moment of crisis where you start to think about the impacts of AI on the world and how to develop AI in a more responsible way. And you might find yourself with a choice. Should I go for those deep technical problems that initially drew me to the field, or should I pivot to these socially important problems that seem so critical in this moment? And the thing that I've learned from Olga's work is that you don't have to choose. In many cases, in not all cases, but in many cases, responsible AI development actually requires pushing the technical state of the art in many ways, and Olga has excelled at doing that. In addition to her work on computer vision and AI fairness, she also cares deeply about not just fairness of AI as a technology, but fairness of AI as a field in terms of who gets to be an AI researcher. And I think she's going to talk about her efforts in that regard as well as a leader of the AI for All program. I could read out a long list of her accomplishments and awards, but instead of cutting into her time, I'm going to turn it over to Olga.
Oh my God, thank you so much, Arvind. That was an amazing introduction. All right, okay, so let me share my screen here. I love seeing all of you. I love that this is not a webinar, so I can actually, see faces or at least sort of see photographs, even if you turn off video. So we'll talk today, right, about fairness in visual recognition, about data sets and the models and the leadership, as Arvind alluded to. So I'll sort of dive in and I'll pause for questions at sort of key points in the talk, and definitely feel free to jump in. And I'm doing more breadth rather than depth today because I kind of, I know we have a very diverse audience, and so part of my goal is sort of to tell you the kinds of things that we've been working on, and then sort of be able to, dive deeper into any of those as there's interest in the room. So there we go. So a few years ago, right? So when computer vision, for a while, computer vision just didn't really work. So it was kind of used in things like, it would sort our mail since the late 90s, but otherwise the technology just wasn't quite ready for real-time deployment. And then a few years ago, it started being used all over the place in all kinds of settings. And as that started happening, we started realizing all kinds of problems with it. So there was, computer vision model that learns to quote unquote increase attractiveness by manipulating skin color. So this was somebody decided to use it for the application of increasing attractiveness, which is a whole other thing. But putting that aside for a second, what it was doing is manipulating skin color. And this was, one question was why was this happening? There was machines that were taught by photos learned a sexist view of women. Facial recognition is accurate, but only if you're a white guy. And so this raised all kinds of very deep and complex questions. And I suspect many of you have thought about this in sort of much more depth that I have about the kind of impact and the root causes of this behavior. And so, for example, many of you might have read Ruha Benjamin's recent book, Race After Technology, right? That really takes a very deep look into these behaviors and their impact on the world. But for the purposes of this talk, I'm actually going to simplify this, right? Because I want to talk about sort of how we take technical pieces of this and sort of break it up into technically, manageable chunks, and then sort of start breaking away and kind of chipping away at this bigger problem. And so the simplification here is we're just going to say, okay, there's some human history biases and prejudices out in the world. That makes its way into the large-scale data that we're using to then train our models. The models are learning from the data and absorbing some of the biases. The models then get used to make decisions, and then that becomes part of our history and part of our world. And so the question that we ask, right, in my lab is, can we adjust the AI design to mitigate these effects? So how could we bring our technical expertise into sort of making an impact on this cycle? So let's start by first talking through the large scale data piece. So what can we do on the data side? So the key thing, right, with large scale data is, so computer vision models are trained with millions and millions and millions of images. That is how we develop this technology. That is how we know how to build visual recognition. But the key thing, right, is that large scale data does not necessarily mean fair representation. I suspect I'm preaching to the choir here, but I'll anyway sort of point out a few works. So one is, of course, a seminal work by Joy Blumwini and Tamia Gebru in 2018, sort of pointing out the lack of race diversity in face data sets that were used for training face recognition technology. Perhaps sort of more subtly, we've looked at things like geographic diversity, right? So these data sets, it's not just about the demographics of people in them. There's also, as a result of the way that data collection happens in computer vision, there's, if you look at the map of the world, you look at where are these images actually coming from, where are they being collected from in the common computer vision data sets like ImageNet or Open Images that you might have heard of. These data sets are very US centric, with some coming from Europe and so on, but continents like Africa are essentially entirely unrepresented in these data sets. And this leads to some very interesting finding, very interesting behavior, that even if you work on problems within computer vision that have seemingly nothing to do with people, you're working on something like object recognition. So it turns out that this lack of geographic diversity is still very relevant, because you end up getting models that, for example, learn to recognize US brands of liquid soap as soap and fail to recognize bar soap, because it turns out that even though bar soap is the way that soap is used in the vast majority of the world, the data sets come primarily from the US. The US has particular brands of liquid soap, and that's what the models use. And so a lot of these kinds of issues can then be traced back to the fact that we're collecting all of this data primarily from the web, because it's the cheapest, most readily available, largest scale source of data. And there's tons and tons of work analyzing the lack of diversity in image search engines. So things like if you query for a term like CEO, you get back photos of primarily white men in suits, and that is obviously a very biased and very particular view of this term. And so when all of computer vision data sets are constructed by querying the web, obviously you get these kinds of highly undesirable effects there. So what can we do? So we're kind of coming at it from the perspective of having collected a lot of these computer vision data sets, and sort of thinking about, practically speaking, right, what are the constructive solutions we can come up with to try to mitigate some of these effects now that we're aware of them. And so our first line of work, so this is led by a student. I'll be sort of calling out the various students that worked on the project. So this is Kai Yu Yang, he's a PhD student in computer science here. So this is work looking at the ImageNet data set that many of you might be familiar with, but let me kind of give you the 30-second version of ImageNet in case you aren't. So ImageNet is a data set of 14 million images illustrating 20,000 visual categories. So these categories are obtained from WordNet, which is a lexical ontology of English nouns. So every node in WordNet is a particular category, and then these categories are illustrated with images. Like, for example, on the right, you see there's hammer, and there might be pictures of hammer, there's cup, pictures of cup, and so forth. These are all images collected from the web and then cleaned up using crowdsourcing. So it's a standard benchmark for visual recognition, for trying to figure out, is my algorithm for recognizing objects in the world better than somebody else's algorithm, so for measuring accuracy on this task, but also used for transfer learning to a wide range of applications. So if you think about computer vision being deployed to do image captioning, for autonomous driving, for depth estimation, so a lot of this, a lot of the technology, actually the back end of it it's a deep learning model that's trained on ImageNet first, and then fine-tuned or adapted to this particular task. And so the impact goes sort of far beyond just the single benchmark, but actually affects a lot of downstream applications. So our first two kind of lines of work, our first two papers here, we look at the ImageNet data set. And the first one, we're looking at the person subtree within ImageNet. So again, it's 20,000 different categories. organized according to a lexical ontology, and so there's a particular subtree of this ontology corresponding to to people categories. And so there are categories like conversational partner, ancient, groom, black belt. And so in this work we did that was published last year, the Fairness, Accountability, and Transparency Conference, we did sort of a deep dive into what kind of images are actually being used to represent people, what are the demographic diversities within this data set. We found some categories that needed to be removed from the data set now that we're sort of looking at it more deeply, because these categories might have made sense in WordNet, but no longer make sense in ImageNet. So there might be categories like pacifist, which is a totally reasonable English noun, but you can't really illustrate it with photos. And so this is an example of like a deep dive into a particular data set, sort of thinking about what is actually in there. So, however, when you hear about ImageNet, chances are what you're actually hearing about is ImageNet Challenge. So this is a subset of ImageNet with 1,000 categories out of the 20,000, illustrated with 1.4 million images. So about an order of magnitude less than ImageNet as a whole. And these are particular objects like barber chair, like husky, like beer bottle, which are sort of generally unrelated to any people category within ImageNet. So the people subtree is by and large not actually used in ImageNet Challenge. However, there are still, because those data is collected from the web, there are still people in these images. And so one question that we asked, right, is like, can we do something to help protect the privacy of people in this data set? And so one of the things you might think, well, okay, if there are privacy concerns, maybe we just scrap this data set entirely. But the reality is that this data set is so commonly used right now in computer vision. Like if we scrapped it, so this is a data set that we collected. I was part of the team sort of collecting them when I was a PhD student at Stanford. So even if we scrapped it and if we say we're no longer hosting it, the reality is all of the computer vision community is very, very heavily relying on it. And so what we ended up doing is sort of taking small steps towards mitigating some of the concerns, in particular by annotating all of the faces of people in the data, so sort of annotating where the faces are, and then blurring or obscuring these faces, and then essentially ensuring that visual recognition accuracy, so the ability of models to predict whether this is a photo of a barber chair or a husky or a beer bottle, remains unchanged. And so in that way, we're kind of providing a slightly cleaner, a slightly better version of this data set to the community, because again, it's kind of, it is largely outside of our control at this point to just pull it entirely, but this is kind of taking one small step towards making it a more responsible data set. So, however, all of these kind of analysis, right, we're looking at a particular data set and spending, a lot of time and effort originally on collecting it and now on kind of cleaning it up or making it better or fixing some of the errors in it. But thinking much more deeply, so this is work with Arvind as well as a PhD student, Angelina Wang, is thinking about, can we develop some tools that will assist dataset developers and users in the future with regard to kind of understanding what is hiding in these visual data sets. So the trick with ImageNet, right, it's 14 million images. We can't look at it manually. We can't manually examine it. Some of the more recent data sets are even larger than that. So how do we think about what are the kinds of biases, what are the kinds of issues that might be hiding in the data set, and how do we empower dataset creators to sort of take responsible steps here? And so some of the contributions of this work, now this was published in a computer vision conference last year, trying to aid dataset creators and users by revealing biases in large-scale visual data. And so this tool leverages the available annotations, existing vision models, census data, to identify bias in the representation of objects, of people of different demographics, and of geographic regions in this data. And it suggests actionable insights to the user. So let me give you one very quick example. So here we're looking at images from the COCO dataset. Some of you might be familiar with it, some not. It is basically a set of Flickr photos of common scenes that you might see in your everyday life, both indoor and outdoor, annotated with objects that that appear in those scenes. And it's used for visual recognition, it's used for image captioning. It's sort of becoming one of the most popular data sets in computer vision. So on these scenes, right? So again, we have something on the order of 1 million photos. This data set comes with some object annotations. It's also, we have access to inferred gender of people in these images. And so here is with a lot of the fairness literature, right? So I'm going to simplify gender down to binary. So I'm going to say male or female. These gender annotations are far from perfect. And certainly these ones that we're using here are definitely imperfect because they're derived from image captions. This is actually not even directly annotated gender. I can talk a lot about this, but let me just say that supposing we have some kind of imperfect proxy for gender of people in the photos, and along with this, we also have a deep learning model that can predict scenes in this in these photos. So on the y-axis here of this graph, you see 16 different types of scenes that these photos might belong to. So it might be a scene with mountains, it might be a scene with water, it might be an industrial construction scene, it might be an outdoor transportation scene. And so given access to these annotations on the photos and given access to these predictions from the model, the tool can automatically sort of produce this kind of graph that summarizes the statistics of which genders tend to occur more or less frequently with the different scenes. And so one of the things that you might notice here as a dataset creator or as a dataset user sort of looking at this output, that it appears that the scenes of outdoor sports fields and park contain more males than females, and scenes of shopping and dining contain more females than males. And so an example finding, right, that would be produced by this tool is that in the COCO datasets and particular datasets, men and women are typically depicted with different objects and different scenes. So I'm not going to dive more into this. So again, I'm trying to do sort of breadth versus depth, but you can imagine as a dataset creator, this might be something you might want to know, right? This might give you pause about sort of, is this what you intended to be? Is this how you intended your data set to be or not? And one particular example, right, is if you're supposing you're collecting an autonomous driving data set, and this, you run it through Revise, and Revise says, oh my God, all your photos come from one particular geographic region and comes just from New York. And you might say, well, right, I had actually intended that. Like, that's not a bias in the data set. That's my intention with it. Or you might run through Revise and say, oh my God, all your photos are photos of women. And you're like, right, that was my intention in this data set. But it might also reveal sort of some things that you might not have been aware of, and some patterns that might particularly be problematic. So there is a number of interventions, right? So these are kind of some examples of how we've taken small constructive steps towards trying to mitigate bias, try to mitigate privacy issues in these data sets. But of course, a lot of the time, the reality is that the data set reflects human history. It reflects the realities of our world, right? So if you, a lot of the time there's questions about like, what is a fair representation in this data set? Is it, if it's sort of representing the world as is that really a data set problem, or is it more of a sort of realities of our world problem? And so we turn our attention to thinking about, given that the data will be likely imperfect, and sort of no matter how much we try to make a perfect data set, that's just not going to be possible for a whole range of reasons. So we turn our attention to thinking about what can we do on the AI model side to try to adjust the design of the model to mitigate some of the biases in the data. So I'll pause here for a couple of minutes if anybody has any quick questions on the data before I move on to the models. Okay, excellent. Let me keep going.
I have a question, Olga.
Yep, go ahead.
Yeah, you mentioned that like a fair representation is kind of a hard concept I guess I have so in social science, we have this idea that if you can have a list of every possible person and then you know people's probabilities of inclusion, you can come up with definitions of representativeness from that. Is there some equivalent idea of like the set of every possible image of a cup? It seems like there's no kind of universe that you can sample from, separate from the problems of historical bias. So I guess I'm asking, like, separate from the historical problems, is there even a notion of what it would mean to be a representative data set?
So honestly, I don't think so. I think people are struggling with this. Like there's a lot of the questions that are arising is like, so it's true. So we've known there was a seminal paper in 2011 that kind of pointed out that computer vision data sets are all biased because they're drawn from a particular, every one of them is drawn from a particular bias distribution of the real world. So they're sort of pretending like we're, even, right, ImageNet, we say, okay, we have photos of all objects in the world, but like that's not true. And also the photos are Flickr photos of these objects and photos from search engines, right? That does not necessarily reflect what visual patterns the computer vision system might see. So yeah, I don't think there is it depends. In some applications, like if you're building autonomous driving computer vision, right, the universe of visual inputs it will see is very different than internet photos, for example, and you can sort of talk about sampling from that distribution, but no, I don't think there's like a one grand distribution of visual inputs that yeah, we're basically trying to approximate it in imperfect ways.
Thank you.
Yeah. All right, so let's talk through some of the model things. So what can we do on the modeling side? So there's a lot of different challenges in building fair models, right? So there is kind of the more standard things of just learning with long tail distributions. This comes up outside of the fairness context as well, sort of all over in machine learning. It's like, yes, there's more example of some categories than others. How do you go about training models with that? There's questions around interpretability. So building more interpretable models that are less black box than the standard deep learning systems, being right for the right reasons, right? So if you're making a prediction, are you making the prediction based on the right sort of reasonable input features, or is it because the prediction is biased in some way? Understanding bias propagation, so how bias from data propagates into the models. Quantifying fairness, so how do you even measure fairness? And of course, what are you even measuring when you talk about fairness measurements, or when you talk about sort of things you might be measuring with machine learning in general. And then a lot of very nice literature on kind of studying the history of machine learning fairness. And so again, in the spirit of breadth versus depth, I'm going to give you kind of three, I'll talk about 4 papers, but kind of 3 lines of work that we've done in this space. So the first one is the most recent, actually, on thinking about understanding and evaluating racial bias in image captioning. So this was led by Dora Zhao, who is a master's student, and Jelena Wang, again, who's a PhD student. And so our goal here is to understand whether and why racial biases exist in image captioning system, right? So an image captioning system, you're given, you're trying to build a system that, given a photograph, can describe it in natural language. And so we made kind of 2 key contributions here. So one is we annotated skin color and perceived gender expression of people in the COCO 2014 validation set. So again, this is the COCO data set that I used to show the example with the revised tool. So before the demographic annotations that people were using on this data set actually were sort of derived from image. It's a whole other story, but basically they were not annotated directly. There were a number of errors here. So in our annotations, right, so these are IRB approved crowdsourced annotations. Also, of course, definitely not perfect, but at least on the whole, hopefully better, and thus allow us to kind of study overarching patterns a little bit better in this data. And this is available for academic use. And then we took a dive into analyzing pathways of bias propagation. So one of the things with image captioning, right, is you kind of never know even if you're, so when you look at the automatic captions, right, so there's some use of racial descriptors and offensive language that we saw in the automatic captions. There's differences in accuracy between captions that are produced on photos of people of lighter skin versus darker skin. There's differences in caption content that's being produced. And one of the questions that we asked, right, is like, is this due to the differences in visual appearance of the images? So you can kind of ask yourself, you know, outside of the person's skin tone, but like, are the Cs that they're depicted in different within the data set? Or also, is it due to the manual caption? So the way that people who were providing this training data were describing the photos. And so in the manual captions, we observed, again, in this data set, there was a use of racial descriptors and slurs, and many other works have sort of noticed this as well. And that there's differences in caption sentiment and content. And so one of the example findings that sort of came out of this is that even after controlling for visual appearance, so sort of normalizing for, we're basically finding pairs of images which are very similar, except for the skin color of the person depicted. The captions differ in word choices used to describe images with lighter versus darker skinned individuals. And what's sort of particularly interesting here is that this is particularly apparent in the manual captions as well as in the newer transformer-based models. So this paper actually ended up being somewhat of a call to action to the computer vision community, kind of pointing out that similar to what I'd mentioned before, right? So when computer vision was used for, you know, just for sorting our mail and for sort of no other high stakes applications, right? Bias was not nearly as much of an issue, but now that we're moving into, now that computer vision system actually started working quite well, accuracy started being higher, it started being deployed all over the place. This is where some of the bias and fairness issues are coming up. And so similarly in this paper, we sort of say, okay, actually, it seems like the older image captioning systems describe very generic things about the image. So they sort of say, this is a person playing tennis. And they will say this, you know, no matter how much the photos differ, if there's any cues for tennis, it'll kind of just say, okay, there's a person playing tennis, and that's it. And it's producing not very descriptive captions, which have correspondingly a lot less bias, is just kind of stating something very generic. But as these captioning systems are starting to become better, they're starting to be able to describe the image in much more depth and much richer language. That's when we start seeing some of these bias issues. And so we're kind of pointing this out to the community that, like, this is the kind of stuff we need to watch out for, particularly, you know, before we start deploying these systems. So this is sort of one recent line of exploration, right? So we're analyzing really pathways of bias propagation. A you know, somewhat related question to this is, as we're talking about bias propagation, so how do you even go ahead and quantify it? Like, what does it mean for there to be bias in these systems, and how do you think about it, particularly for bias amplification, right? So I've mentioned we might have bias in the data itself, or bias in the way that humans have annotated it. And so it's been shown that machine learning models, by virtue of being statistical systems that try to work well on majority cases, will actually sometimes amplify the bias that's in the data. So rather than mitigating it, which is what we would hope to happen, actually, so one sort of concrete example is, suppose you have a collection of images where every time you see where photographs of computers frequently occur so in the photographs, computers 90% of the time occur next to women and 10% of the time occur next to men. So your computer vision systems, right? So ideally, you would still be able to recognize, computers would still be able to accurately recognize, you know, men or women in the photos. But in practice, what might happen is the computer vision system will say, okay, actually, I'm going to, you know, it's too difficult for me to recognize computers. So what I'm going to do is take this shortcut where anytime I see a woman in the photo, I'm going to predict that there's a computer next to it and next to her. And anytime I see a man, I'm going to say, okay, there's probably no computer in this image. And so in that way, whatever, you know, 90% bias existed in the data, now it becomes amplified by the model. And so our contributions here, so this is published in a machine learning conference this year, is to propose a new metric to measure the amount of bias in the models compared to the bias in the data. So let me walk through this equation just very quickly to give you a sense of this, right? So what's happening here is we have a set of target labels. So this is like predicting, like, is there a computer here? Is there a, I don't know, is there a lamp in this photo? Is there a car in this photo? And a set of protected attributes. So this is gender, for example, labels. So we're averaging over the pairs of target labels and protected labels. So we have a binary indicator y sub at, which basically says, is this, is the presence of women, so let's use gender as a protected label, is the presence of women positively or negatively correlated with the presence of a computer? So this is y at, and then delta at, then, so if we look at the top part of this, so this is the probability that t hat is prediction of this target label. So probability the computer is predicted given there's a woman in the image, minus the probability that there would actually be a computer given there's a woman in the image. So the question is, is the predicted probability higher than what we would expect based on the data statistics? And so this is if you're measuring the bias amplification from the presence of a woman to the presence of a computer. So this is if you're measuring the A to T bias amplification, and then it's vice versa if you're also making a gender prediction. So you're trying to understand how much the presence of a computer influences the probability of the person being predicted as being a woman. And so basically we're formulating, right, a new equation for measuring bias amplification. Then we analyze it in various diverse applications. And again, without diving too much into depth here, but very happy to chat about all of this, and Angelina, I'm sure, is as well. So some of the example findings that prior strategies for mitigating bias amplification in the models actually fail under the new metric when you sort of properly measure and properly decouple the directions of bias amplification, also kind of address some of the failures in the previous systems. And so last but not least, right, so I want to talk through some of so the next two papers and sort of the final two technical papers that I want to sort of highlight here look specifically at actually building deep learning classifiers, and so exploring techniques for training classifiers on data with spurious correlations. And so these are both published in computer vision venues again. So the first one was called Towards Fairness in Visual Recognition, so looking at effective strategies for bias mitigation. So our contributions here is to propose a simple data set with controlled biases, to analyze multiple bias mitigation techniques and validate them in more realistic benchmarks. And so, you know, part of the kind of mindset here is that it's very, again, it's very difficult to tackle the issue of fairness. Generally, it's very difficult to kind of understand when you have you know, particular behavior in a deployed computer vision system. It's very hard to like dial it back and kind of figure out where is all of this coming from. And so here we're trying to simplify this down to a setting where we can control the biases. And this is, you know, we artificially introduce some correlations in the data set and then run a whole slew of analysis of kind of how do we, so the kinds of biases here, right, is similar to what I've already been talking about. So like the presence of computers correlated with a particular gender, or the presence of some particular visual structures correlated with another one. And so we run a whole slew of analyses for like how to train models with without capturing these correlations. Turned out to be much harder than we expected because deep learning models are very difficult to control. And so some kind of example findings here, right? Again, without diving, you know, into all of the technical details. So you might think that over undersampling is the right intervention strategy, right? If you just have more examples, you know, if you have some kind of correlation in the data, well, you can just over or undersample it to remove that correlation. So it turns out it's prone to overfitting and numerical instability, and other people have found this as well, but we've kind of revisited that in this setting. So may not work very well, particularly when you have high degrees of correlation, particularly when you have sort of high degrees of bias. Adversarial debiasing is a strategy that's been proposed in the literature that sort of says, okay, so you see the sort of T-SNE plots on the right without adversary and with adversary. Let me just explain it at a high level without talking through the plots, right? So the idea is I'm going to train a visual recognition system, and I'm going to add a term to the loss function that makes sure that this system does not learn any features that would be predictive of gender. So I want to train a system that can recognize, computers or lamps or cars in photos, but I'm going to ensure that, so because these systems work from the pixel level directly to output, it's sort of complex multi-level function that with a ton of learnable parameters that then at the end outputs a prediction. So I'm going to impose a constraint on the parameters of this function such that the intermediate feature representation that is learned is not predictive of gender, or is not predictive of sort of some kind of protected attribute that I wanted to be invariant to. And so it turns out that what happens when you do that, even though a lot of the literature seems to suggest that this is a reasonable intervention, but in computer vision settings in particular, basically you end up training a very poor classifier. So long story short, if you try to do this kind of intervention, your accuracy suffers a lot, kind of to the point where it becomes essentially unusable in a lot of cases, because it just, the visual representation becomes incapable of actually doing the discrimination task that you want it to do. And so it turns out that, right, so what we propose, and I guess what we sort of show, I mean, it's not a particularly new method of domain independent training, which basically is you're training separate target classifiers for each protected attribute. So that turns out to be much more effective at mitigating these spurious correlations than sort of even more complex techniques like adversarial debiasing. And so in a follow-up work to this, then again, kind of diving even more technical. So we're still trying to develop a method for training visual classifiers on data with spurious correlations. But here we're actually trying to generate the data. So rather than just working with the data set that we're given, we're actually trying to use what are called generative adversarial networks to develop a data set augmentation strategy where we can actually augment our real world data with some kind of synthetically generated data to try to remove particular correlations that we want our model to be invariant to. And so here we've demonstrated improvements in fairness over prior art, and also analyzed the Celeb-A benchmark, which many of you may be familiar with. It's a very commonly used benchmark for sort of face analysis and also for a lot of the fairness research. And so we were able to show that you can train classifiers with similar amounts of accuracy. So AP here, that's average precision. That's basically a metric of like how well your model is doing. So with very similar levels of accuracy, while being better on 3 different fairness metrics, including BA, which is the bias amplification metric from ICML that I'd mentioned previously. And so again, without diving into the technical details, so the example finding is that it turns out, so a lot of the prior work would use kind of multiple generative adversarial networks, multiple GANs to do this kind of augmentation. Turns out a single GAN is actually sufficient here. So the key to keep in mind here with this sort of synthetic data generation is that, so we demonstrated this on a data set of photos of faces. And so faces are very structured, and it is easier to do sort of synthetic data generation with faces. But when you start talking about things like, much more complex real world scenes, doing automatic generation, especially with GANs, is just very challenging. And we're sort of starting to get there, but it's somewhat outside of the scope of what these models can do right now. And so this is, an intervention that works well in a relatively constrained setting. So that's kind of a very quick run through the kinds of interventions that we can do on the data side, on the model side. So I do want to, so as Arvind alluded to, I do want to finish the talk by talking a little bit about the sort of fairness in more general, and particularly sort of fairness and representation in the AI decision makers. And then I will pause with plenty of time for discussion and questions about all of the technical bits as well. So the key question here, right, is like, you know, I'm talking about all of these interventions that we're building in my lab, and along the way we are making a ton of decisions about, you know, what do we consider to be, you know, important biases to tackle with these problems. There's, you know, we're also building other computer vision systems. We're making decisions about, right, like, where are we collecting the data? What kind of questions are we asking about the data? What kind of models we're building? What are the design decisions in building the models? What kinds of things we think are important to work on? And a lot of these decisions are then having very, very, very important impacts on the development of this field as a whole. And I hope I'm preaching to the choir. I hope you know that. So computer vision, computer science, AI, STEM generally is an extremely homogeneous field. So we have very few women. We have relatively few people of color. We have very, very sort of homogeneous population working on these problems, and this leads to all kinds of biases in the AI decision making. And so a few years ago, so together with Fei-Fei Li, who is a professor at Stanford, who I hope many of you have heard of, and Rick Sommer, who is a director in K-12 education, we started AI for All, which is a nonprofit dedicated to increasing diversity and inclusion in AI. And so at AI for All, we say that AI will change the world. AI is already changing the world. It is, again, a technology that is revolutionizing basically every aspect of our lives, and is being deployed in all kinds of high stakes application. And the question that we ask is, who will change AI? And so our goal is to educate and support a diverse next generation of AI leaders. So we're really thinking about not just broadening the pipeline, but actually how do you get people from diverse demographics, diverse backgrounds, diverse viewpoints into the leadership roles within AI. And so we've done a lot of our interventions focus early in high school and college. So we've partnered with 16 universities, including, of course, Princeton, to run summer programs for high school students from groups underrepresented in AI. We've launched a free online open learning platform for particular students who may not be able to attend some of these summer programs, but this is partnering with high school teachers and students themselves directly who want to learn more about AI. Created college pathways for students from underrepresented groups who are now in college, who sort of early college, who may not have thought of themselves as wanting to be in this space. And then the students who are excited about continuing in AI. So after they've started through some of these entry points, we're providing lifelong training, mentorship, leadership opportunities, and community events for our alumni. And that is honestly likely the most impactful thing that we're doing, is just sort of sustaining their interest and providing opportunities for these students to stay in this field and to take higher and higher leadership positions if they choose to. And one of my all-time favorite quotes is from a student who attended AI for All in 2016, said, "Until this program, I never thought that people who look like me could succeed in computer science and AI." So this is why we do what we do. So I will pause here, give a huge shout out to all of the students who contributed to all of this work and have led this. So talked about the large scale data, right? So need to reveal, analyze, and mitigate representational bias. About the AI model, so need to quantify, understand, and mitigate bias propagation. And then a little bit about the AI decision maker, so need to diversify the AI leadership. And I'm very, very happy to take questions.
Perfect. Thank you, Olga. And with that, we are out of time. Let's thank Olga one more time for that very stimulating talk and discussion.
Thank you so much.